In the early 1800s, the human body looked like the simplest kind of fact. Flesh felt dense, bone felt hard, blood felt thick. When people cut, stitched or broke a limb, they met resistance every time. So the common picture of matter stayed straightforward. The body consisted of solid substance packed all the way through like wood or stone. Stuff seemed continuous, not broken into pieces. That assumption shaped everything people expected from nature. If you squeezed a muscle, you believed you pressed on fully filled material. If you weighed a body, you assumed the heaviness came from how much solid matter had been crammed into a volume. Even when scientists talked about fluids, fibers, and tissues, they treated them as different forms of the same idea: matter as an unbroken, complete fill. Emptiness belonged outside the body, not inside it. It also set a trap. Because matter seemed continuous, it felt natural to imagine that if you kept dividing flesh into smaller and smaller bits, you still ended up with more flesh, just finer and finer. No missing parts, no gaps, no hidden structure. The body in that view worked like a compact mass, and the world made sense that way. Then new questions began to press in on that certainty. Then a new way of thinking arrived, and it began with a careful English schoolteacher and scientist named John Dalton. He looked at how gases mixed, how chemicals combined, and how reactions always seemed to follow simple counting rules. Something kept repeating, fixed ratios again and again. Dalton treated that repetition as a clue. Matter, he argued, did not behave like an endless, smooth substance. It behaved like it came in units. Dalton called those units atoms. In his picture, each chemical element had its own kind of atom, and those atoms acted like tiny, solid pieces. They could join together in small, whole-number groupings to make compounds, then break apart and recombine in a reaction. That simple idea explained why water always formed with the same recipe, and why changing the recipe made a different substance. Chemistry started looking like arithmetic. That shift mattered for the body. Flesh, bone, and blood no longer counted as one continuous block of stuff. They counted as arrangements. The body became a vast construction made from many kinds of atoms, linked into molecules, then built into cells. It sounded almost too neat, but it gave scientists a new handle on physical reality. If matter came in pieces, then solidity needed a new explanation. By the end of the 1800s, the atom still sounded like the final brick of reality, a tiny, solid ball. Simple, complete. But experiments with electricity began to upset that calm picture. A British physicist named J.J. Thomson studied how electric currents moved through gases at very low pressure. Instead of acting like smooth, invisible flow, the current left clues. Something inside the atom seemed to carry charge and respond in a consistent way. Thomson used a device called a cathode ray tube, and the result kept repeating. The ray bent when electric or magnetic forces were applied. That bend mattered. It meant the ray behaved like a stream of charged particles, not like a wave of light and not like a property of the gas itself. Even more striking, the same behavior appeared no matter what material was used. The particles came from the atom, not from the setup. In 1897, Thomson concluded that these tiny charged pieces were real parts of atoms. They later became known as electrons. That single step shattered the old idea of atoms as indivisible. If an electron could be pulled out, then an atom had an inside. It had components, structure, and hidden space where those components could exist and move. The solid ball picture did not survive. Matter had layers now. In 1911, Ernest Rutherford tested a simple idea with explosive consequences. He sent fast, positively charged particles at an ultra-thin sheet of gold. The expectation seemed safe. If atoms spread their positive charge through their whole volume, those particles should sail through with only slight deflections. Most of them did. That looked ordinary. Then a tiny fraction behaved in a way that should not happened. A few particles bounced back at sharp angles, as if they had struck something hard and concentrated, not something smeared out. That result forced a brutal choice. Either the measurements were wrong, or the atom's positive charge and nearly all its mass sat in one small place. Rutherford followed the evidence. He concluded that the atom had a central nucleus, dense and tight. That one conclusion rewired everything. If the nucleus carried the mass, yet only a few particles ever hit it, then the nucleus had occupied almost none of the atom's volume. The rest of the atom had not been filled with matter in any ordinary sense. It had been mostly open space, with something else moving through it. The solid atom had turned into a tiny core surrounded by vast emptiness. By 1913, the atom still carried a problem. Rutherford's nucleus sat at the center, but nobody could explain how the surrounding electrons stayed in place. A young Danish physicist, Niels Bohr, stepped in with a bold rule. Electrons did not drift anywhere they wanted. They occupied specific orbits, like fixed lanes, each with a set amount of energy. It sounded simple. It changed everything. Bohr's picture gave scale to the atom. It let scientists talk about distances, not just parts. The nucleus, it turned out, was unimaginably small compared to the atom as a whole. If the nucleus was reduced to a tiny dot, the electron orbits sat far out, leaving an enormous gap between. Most of what an atom was, by volume, was not the nucleus at all. It was space. And that space was not an abstract idea. Every cell in the body was built from atoms arranged into molecules, and those molecules kept their shape while being mostly separated by these vast internal gaps. The body still behaved as solid, but its building blocks did not resemble packed pebbles. They resembled tiny centers surrounded by distance. The shocking consequence landed hard. In every cell, almost everything was empty space. By the mid-1920s, Bohr's tidy picture of electrons circling like planets started to fail. The math worked for a few cases, then broke down. New experiments showed electrons did not behave like tiny balls on clear tracks. They acted like waves sometimes, particles at other times, and always a little unpredictable. The old idea of an orbit, one path, one location, stopped fitting what nature actually did. Quantum mechanics replaced the orbit with something stranger, but more accurate, a probability cloud. Instead of saying where an electron was, it described where it was likely to be. The electron spread out as a pattern, and the pattern followed strict rules. Certain shapes appeared. Certain energies were allowed and others were forbidden. The empty part of the atom suddenly looked organized, like space with a built-in blueprint. That shift changed what mostly empty space meant. It no longer sounded like a hollow shell with little bits flying around inside. It sounded like a region where matter behaved as chances, not certainties, where the space itself carried structure through those quantum rules. The atom still held a tiny nucleus and a huge volume around it, but that volume was not nothing. It was a governed space. In the early 1930s, a new piece of the nucleus appeared. James Chadwick identified the neutron, a particle with no electric charge, hiding in plain sight. That discovery changed the picture of what sat at an atom's center. The nucleus was not just positive charge with electrons around it. It was a tight mix of protons and neutrons, and suddenly scientists faced a sharper question. What held that cramped core together? The numbers did not make sense with ordinary ideas. Protons pushed each other apart, yet nuclei stayed intact. The answer came as another force, strong enough to overpower electric repulsion at very short distances. Neutrons mattered because they added mass without adding extra charge, helping that balance work. Empty space started to sound misleading. Inside the atom, stability came from invisible rules and invisible pulls, not from little chunks packed wall to wall. By the 1940s through the 1960s, physicists pushed further and began treating particles as ripples in fields that filled space everywhere. This was quantum field theory, and it turned the old question on its head. Matter did not sit inside emptiness like beads in a box. The space itself carried ingredients, electromagnetic fields, nuclear forces, and quantum effects that never switched off. What looked empty still acted busy enough to build, shape, and hold together a human body. Modern biology and chemistry had faced an awkward question. If atoms had contained so much room, why had a hand still felt solid, and why had bones still held shape? The answer had not been that the body had been tightly packed with hard pieces. The answer had been force. When atoms in skin and bone had been pushed together, their outer electrons had met first, and those electrons had carried the same electric charge. Like charges had repelled, that electromagnetic pushback had risen fast long before any nucleus came close. It had acted like an invisible spring, turning approach into resistance. Chemistry had depended on that same rule because bonding had only happened at certain distances and arrangements. Press closer than that, and the repulsion had surged. Solidity had been less like stacked bricks and more like two strong magnetic fields refusing to overlap. Then, quantum mechanics had added a second lock on the door. Electrons had belonged to a family of particles that refused to share the same quantum state, a rule called the Pauli exclusion principle. In the body, that rule had forced electrons into separate slots, building layered structure in every atom. Try to compress tissue, and there had been nowhere easy for those electrons to go. The body had stayed rigid, not because it had been full, but because the rules had blocked collapse. A simple test helped the scale click in the present day. One atom got inflated in the mind until it matched a big sports stadium, about 100 meters across. At that size, the nucleus did not become a marble. It shrank to a speck near the center, closer to a grain of dust than anything solid. Almost everything in between stayed open. Then the electrons got placed where they belonged. They did not form a neat shell or a wall. They occupied a wide, fuzzy region, scattered as chances rather than hard beads. So the stadium did not fill up with parts. It stayed mostly unoccupied volume, with forces and rules doing the heavy lifting. The structure existed, but the stuff barely took up space. That scaling did not stop at one atom. Every cell, every molecule, every protein followed the same layout. Tiny cores, wide gaps, and interactions across them. When all those stadiums got stacked into a body, the arithmetic turned brutal. By volume, matter took up almost nothing. The body worked out to about 99.999999% empty space, even while it still felt solid. By the end of this trail, the conclusion felt almost rude to common sense. In the early 1800s, a body looked like solid meat and bone, so it seemed made of solid substance all the way through. Yet the modern picture had pushed in the opposite direction. The stuff of a person did not fill most of their own volume. Most of it counted as space. That did not mean a person had felt ghostly or hollow. Hands still met resistance. Feet still pressed the ground. The surprise came from what physics had said, that resistance really was. It had not come from little hard chunks touching like stones. It had come from rules and forces acting across gaps, electric pushback and quantum limits that stopped atoms from sharing the same state. So the everyday feeling stayed the same, but the explanation had flipped. What once looked like continuous packed matter had turned into a thin pattern, nuclei taking up almost no room, electrons spread as probabilities, and fields holding everything in place. The body still registered as solid to the senses, yet in the language of physics it had been mostly space, structured and governed by quantum rules.